All right, welcome to section 2.5. Talk about continuity today. All right, so continuity. The limit of a function as x approaches a, so remember that was that notation we talked about last lecture, can often be found simply by calculating the value of the function at a. Now I know, remember we said, well, we're really not concerned with what's happening at x equals a, but if we had a few circumstances, right? Remember, if you have a polynomial or a rational function, and as long as a is in your domain, then you're allowed to plug in. All right, so functions with this property are called continuous at a. So we will see that the mathematical definition of continuity corresponds closely with the meaning of the word continuity in everyday language, right? A continuous process is one that takes place gradually, without interruption or abrupt change. It's like, when you grow, right? You're just a little tiny baby and you grow into an adult, but it's an incredibly slow but continuous process, right? You don't jump from 3 feet to 5 feet overnight. Okay, so definition, here we go. So a function is continuous at a number a. So remember, a is again an x value. Make sure you know that. So a function f is continuous at a number a if the limit as x approaches a of the function equals f of a. Okay, so as long as the function value at a equals the limit as x approaches a, then we've got continuity. Now, this three-part definition down here is what you really want to make sure you know. 100% guarantee you there will be quiz and exam questions on this stuff here. So it's very important. Let's see. So notice that definition 1, the one we just talked about above, implicitly requires three things if f is continuous at a. And again, all three of these things have to be true, not just one or two. All three must be true to have continuity at some number a. Okay, so number 1, f of a is defined. In other words, a is in the domain of f. In other words, if you plug a into the function, you get a valid answer. Number 2, the limit as x approaches a of f of x has to exist. Right? If it doesn't exist, then how could it be equal to the function, right? And of course, number 3, basically what they're saying is number 1 and number 2 must be equal to each other. Okay, so f of a must be defined, the limit as x approaches a of the function must exist, and those two values must be equal. If that's the case, if you have all three of these situations, you have a continuous function at that x value a. All right, so the definition says that f is continuous at a if f of x approaches f of a as x approaches a. Thus, a continuous function of f has the property that a small change in x produces only a small change in the y value. In fact, the change in f of x can be kept as small as we please by keeping the change in x sufficiently small. If f is defined near a, in other words, f is defined on an open interval containing a, so these open intervals, make sure we know again, we're talking about x values. Okay, that interval they're talking about here are x values, an x interval. Containing a except perhaps at a, that's that limit definition again. We say that f is discontinuous at a or has discontinuity at a if f is not continuous at a. So that's a pretty easy definition. If it's not continuous, it's discontinuous. Physical phenomena are usually continuous. For instance, the displacement or velocity of a vehicle varies continuously with time, as does a person's height, like I was talking about before. But discontinuities do occur in such situations as electric currents, right? So AC/DC, not the band, the electricity, but AC, alternating current, right? DC, direct current. Let's see, geometrically, you can think of a function that is continuous at every number in an interval as a function whose graph has no break in it. So you might remember this definition from back in algebra, right? A continuous function is where you put your pen down and you can draw this function, whatever it looks like, without lifting your pencil. Okay. Let's see. So example 1 here. Let's see. The figure below shows the graph of a function f. So this whole thing, all this blue, is the function. All right. at which numbers is f discontinuous? When they ask you that, at which numbers is f discontinuous, they're asking for x values. Okay? So let's see. Discontinuous is we'd have to lift our pencil, right? So we can see, well, definitely right there we'd have to lift because that open circle means a hole, right? So that's x value of 1. We can definitely see right here we have a jump in the function. So that's x equals 3. And another jump right here at 5. Okay? And like I just said, because we have holes and jumps, that's why it's discontinuous. Okay? All right. So example 2, so that's graphically. Let's look at algebraically. So example 2, where are each of the following functions discontinuous, right? In other words, where they not exist, where are they undefined? So A is definitely a rational function. We should be used to this by now, right? We went over it in chapter 1. There was a test question on chapter 1 as well about these kind of problems. So what we do, the process is you take the denominator, in this case x minus 2, set it equal to 0, and solve for x, so x equals 2. So if we plugged in a 2 into this rational function, we would get a undefined value, right? So there'd be a hole in the graph or a jump somewhere. Either way, this function is discontinuous at x equals 2. All right. Another way to check, so that's part A. Part B, another way to check to see if you have discontinuity, right, any breaks, jumps, things like that, is to use limits. Okay, so let's use limits, and let's use that 3-part definition of continuity we just talked about. All right, so look at this function here. We're on B. Okay, so it's a piecewise function, 1 over x squared if x is non-zero, and 1 if x equals 0. Okay. All right, so let's see. Let's first find the limit as x approaches 0 of the first part there, 1 over x squared. Well, this is a little weird, right? Limit as x approaches 0 of 1 over x squared. So we have to analyze this, right? We can't plug a 0 in, right? So let's ask ourselves the questions, right? We do have a rational function, but 0 is not in the domain, so we cannot plug in, right? So we've got to use logic on this one. Now, as x approaches 0, what's happening to 1 over x squared? So a little side note here. Let's think about that. In other words, the denominator is getting smaller, right? As we approach 0, it doesn't matter from the negative side or the positive side, but either way, as we approach 0 from either side, the values are getting smaller. So think about a fraction. What happens to a fraction when the denominator gets smaller? Well, if you're not sure, use an example. Let's see, 1/5. Let's make that denominator smaller, 1/4. Let's make that denominator smaller, 1/3. Keep going, 1/2, 1 over 1. What's happening to the value of the fraction as the denominator gets smaller? Right? Isn't that value going up? Okay, so what we've got to think here, though, is we're approaching 0. In other words, we're going to get infinitely close to 0. So if we're getting infinitely small in the denominator, the fraction is getting infinitely large. Okay? That's an important concept. You're going to be using that quite a bit in this class, especially this chapter with limits. Okay, so here we go. The limit exists, right? We just found it. But we have to see if f of 0, right, f of a, in this case, a is 0. What's f of 0? Well, it says right here, f of 0 equals 1, right? So we have f of a exists. We have the limit as x approaches a exists. That's the first 2 parts of that continuity definition. But the issue here is 1 and infinity are definitely not equal, right? So we have discontinuity or discontinuous at x equals 0. All right, because it does not fit the three-part definition. Okay, moving on. Let's do part C. We'll do the same test here. We want to check, find if the limit exists, find the function value, see if that exists, and see if they're equal. So let's see what we got. All right, so we're going to find the limit of the top part here. So the limit, again, make sure you use proper notation so you don't lose points. Okay, oops, limit as x approaches 2, right? Because that's our value here. Okay, well, we have a rational function, right? Remember, we ask ourselves the questions, is it rational, polynomial? This is definitely rational, but the problem is 2 is not in the domain. If we plug a 2 in, we get 0 in the domain. Can't do that. So remember before we had a way out of this, we said, well, what if we can reduce? If we can reduce, then we can try asking the questions again. So x squared minus x minus 2 factors out to be x minus 2, x plus 1. This is all over x minus 2. Well, that works out nicely, doesn't it? Okay. So then we have, I keep forgetting to put that 2 in there. So we have the limit as x approaches 2 of the function x plus 1. Well, x plus 1 is a polynomial, right? The domain of any polynomial is all real numbers, so 2 is definitely in the domain, which means we're allowed to plug in, which means the limit exists, and so the limit exists, so let's check now the function value. So let's see f of 2, right, because we're using that a value of 2. F of 2, well, they tell us right here, is 1. There's a problem, though, right, because 3 and 1 are definitely not equal. So, discontinuous at x equals 2. And you need to write this out. You know, show as much work as I show on these types of problems to get full credit. You need to prove everything. Remember, nothing is taken for granted in this class anymore. Okay? Okay. This notation here, I think we may have talked about it. This is called a step function. What it means is you're always going to round up to the next integer. Or, I'm sorry, round down to the next integer. So we've got, if we were to graph this, this is what it would look like. So those are integers. All right, so this is what it looks like. So you would have a solid dot, oops, kind of hard to see here, to an open dot, next integer, solid dot, to an open dot, next integer, etc. And this would keep repeating. So you can see it looks like a set of stairs. That's why it's called the step function. We can definitely see right there, though, that we have discontinuity at every integer, don't we? So these are, I know I didn't write them in there, but that's 1, 2, 3, 4, etc. Okay. All right. So in each case, the graph cannot be drawn without lifting the pen from the paper because a hole or break or jump occurs in the graph. The kind of discontinuity illustrated in parts A and C is called removable because we could just simply redefine the function at that value, right, to equal the limit value. We could do that if we wanted to. The function g of x equals x plus 1 is continuous, right? That's what we did right there, that work we did simplifying. The discontinuity in part B is called an infinite discontinuity. The discontinuities in part D are called jump discontinuities because literally the function jumps from one value to the other. That's that step function. Okay. All right, definition, another definition here. Function is continuous from the right. So remember, we can take limits from the left and from the right, so we can also talk about continuity from the left or the right. If the limit as x approaches a from the right, remember that notation. Oops. from the right of f of x equals f of a, and it's continuous from the left if the limit as x approaches a from the left of f of x equals f of a. All right, let's see. So example 3, prove the following statement. At each integer n, the function f of x equals step function of x is continuous from the right, but discontinuous from the left. Interesting, huh? Let's graph this again. So we're going to graph this step function. All right, so let's graph this guy. So again, solid dot to open dot. I'm only going to graph a couple of these. I'm not going to do it all. Okay, etc. Right? Okay, so let's use this definition up here. The limit as x approaches a from the right of the function equals the function value at that a value. So, I don't know, let's pick 2 here. Let's let a equal 2. So let's find the limit as x approaches 2 from the right of the step function. Okay, so limit as x approaches 2 from the right. That's coming this way. The limit is 2, right? Okay. And what is, so this is from the right, so what is f of 2 equal to? Well, it's equal to 2, right? Solid dot on there. Okay, so there we go. We just proved continuity from the right? Because these two things are equal. So there we go. Continuity from the right. Let's check continuity from the left. Let's do x equals 2 again. It actually doesn't matter which integer you pick. But let's see. Let's do 2. So limit as x approaches 2 from the left of the step function. All right, so 2 from the left. So we're coming in at 2 from the left. Remember, be careful. I'm talking about a limit, not the function value. The limit is 1. Okay? But f of 2, well, it's the same function as above, so f of 2 still equals 2. Problem is these guys are not equal. Okay? Since they're not equal, right? Breaks that definition there, so discontinuous from the left. Right? And you could write a little statement. You should write a little statement here. Right? So therefore the function is continuous from the right, but discontinuous from the left. Okay? All right. So number 3, a function f is continuous on an interval. As we keep talking about, that interval is an interval of x values if it is continuous at every number in the interval. Well, kind of duh, right? Makes sense. But of course we got to, use some math to figure this stuff out. If f is defined only on one side of an endpoint of the interval, we understand continuous at the endpoint to mean continuous from the right or continuous from the left. Okay? Because on an interval of values, you've got endpoints. Okay, so you can't say it's continuous outside the endpoints because you don't have any values there. All right, so here we go. We're going to show that this function is continuous on the interval from -1 to 1 inclusive, right? Those square brackets means inclusive. All right, so here we go. Let's write this out. Oh, here we go. So if we've got that a is between -1 and 1, notice my inequalities, right? These are not equal to. So we're not going to talk about the endpoints right now. We're talking about every value inside this interval, okay? Not the endpoints yet. All right, so if a is any value between -1 and 1, not including the endpoints, by using limit laws, we have this. So the limit as x approaches a of the function we have here, 1 minus radical 1 minus x squared. That equals the limit as x approaches a of 1 minus the limit as x approaches a of the radical 1 minus x squared. Okay? All right, so let's keep using limit laws. Well, we know this one, don't we? 1 is a constant function, so the limit as x approaches a of the constant function 1, doesn't matter what a is. For all x values, this function value is 1. Now we're going to use the square root limit law. So we're going to say the square root of the limit as x approaches a of 1 minus x squared. Well, 1 minus x squared is a polynomial, right? And therefore a must be in that domain, which means we can just simply plug in. So we've got a limit of 1 minus radical 1 minus a squared. That's the limit as x approaches a of the function that's been given. Okay. All right, so the limit of this function exists. So part 2 of the continuity definition says we need to make sure f of a is defined, right? Does f of a exist? In other words, can we plug an a into this function? Yeah, sure, why not? 1 minus radical 1 minus a squared. Well, look at that. The limit exists at a, and the function value exists at a, and they're equal. Therefore, or thus, or however you want to write that, there we go. Thus, f of x is continuous on the open interval. Remember, we did not check the endpoints yet. We're talking about just every value inside the interval. All right, so we've proven now, and again, this is the proper amount of work. We've proven that this function is continuous inside the interval. Now what we've got to do is prove continuity at the endpoints. All right, now think of this interval. Right, we're in here. We're inside this interval. So what we want to do is stay inside the interval, basically, and catch the endpoints. In other words, what we're going to do is we're going to check continuity at -1 from the right, because we're staying inside the interval, and continuity for +1 from the left, because again, we want to stay inside the interval. Okay? All right, so let's do -1 first. So we're going to use that definition we talked about. So we need to find the limit as x approaches -1 from the right of our function. Okay. Well, we need to analyze this, right? Okay, so let's think. We're approaching -1 from the right. So think of a number line. Here's a number line. There's -1, so that means there's 0. All right, so as we're approaching -1 from the right, we have numbers that are greater than -1, right? Greater than -1, which means, now be careful with the wording here, greater than -1, but if we square that greater than -1 value, we get something smaller than 1, right? Okay, think about that carefully. Okay, so what happens is we're getting something really close to 1 here, something really, really small, or I'm sorry, really close to -1, and then we square it. It's still going to be really close to -1, but it'll be positive, so we'll be kind of like doing 1 minus 1. You see what I mean? We're going to get infinitely close, so this whole piece is going to get infinitely close to 0. Okay, we're coming in from the right, getting close to -1, but bigger than -1. So we square it, we're still, even because we're getting infinitely close to -1, even when we square it, we're infinitely close to 1, but we're squaring it because so it's going to be positive, so 1 minus 1 is going to be essentially 0 in this case. All right? So basically, again, this whole thing is going to 0. Well, 1 minus 0 is 1. Okay? All right, and then we check the function value. So what is f of negative 1? Well, we actually just kind of talked about that. Well, we'll show the work, but 1 minus negative 1 squared. Well, that's a positive 1. 1 minus 1 is 0. Square root of 0 is 0, right? All right, so again, this equals 1. So we have this. The function value exists from the right, or at that a value, and it's equal to the limit from the right. So thus continuous from the right at x equals negative 1. Okay, so now we caught that left endpoint. Let's do the right endpoint now. Positive 1. Everything's the same. The logic's the same as we just did here. So limit as x approaches positive 1 from the left of the function. Same logic, we're approaching positive 1 from the left, so value smaller than 1. If we square that, we're still really close to 1, and then we're looking at 1 minus 1, which is 0 again. So this limit is still 1. Okay? And we know f of 1, well, again, it's the same logic, right? Plug it all in. Well, that's still 1. All right, so the function value exists, the limit exists from the left. So we have continuity from the left at x equals 1. All right, and there we go. That captures everything we need. So we have continuity in between. We have continuity from the left at 1 and from the right at negative 1. Therefore, f of x, f of x, cannot write today, is continuous on the closed interval from negative 1 to 1. Okay, and that's what they asked us to prove. And this is a full proof. This shows every step. It uses the theorems we talked about, the definitions we talked about. You show this much work, you'll get full credit on a problem like this, and with the little statements in there. Okay? Okay. All right, instead of using all these definitions to verify the continuity of a function, it's often convenient to use the next theorem, which shows how to build up complicated continuous functions from simple ones. All right, so here's a theorem. This one's important to know. It's going to help you out a lot. If f and g are continuous functions at a, and c is a constant, so c is just some number, then the following functions are also continuous. So if you already know that f and g are both continuous functions, then adding them together is still continuous, subtracting them is still continuous, multiplying them together is still continuous, dividing them is still continuous as long as your denominator is not equal to 0 at that a value, and taking either f or g and multiplying it by a constant value, it still remains a continuous function. Okay, that's some important stuff. All right, it follows from theorem 4, the one we just talked about, and definition 3. If f and g are continuous on an interval, then so are those, the adding, subtracting, multiplying by a constant, multiplying together, and dividing as long as g is never 0. The following theorem was stated as the direct substitution property. It's the same one we've been talking about, but it's worded a little better, I think. So this is the same thing we've been doing, right? Ask yourself the two questions. Do you have a polynomial or rational function? Then you ask, is that a value in the domain? Well, like we said, with polynomials, the answer is always going to be yes for the domain, right? Because any polynomial is continuous everywhere. In other words, any value fits in the domain from negative infinity to infinity. Part B, any rational function, it's continuous wherever it's defined. In other words, as long as you don't get a 0 in the denominator with that a value. All right, if either of these two things are true, you simply plug in. Okay? All right, as an illustration of that theorem we just talked about, observe that the volume of a sphere varies continuously with its radius because of that formula, right? V of r equals 4/3 pi r cubed shows that the volume is a polynomial function of radius. Likewise, if a ball is thrown vertically into the air with a velocity of 50 feet per second, then the height of the ball in feet t seconds later is given by the formula h equals 50t minus 16t squared. Again, this is a polynomial, right? So the height is a continuous function of elapsed time. It's continuous. Again, you're not going to go from 3 feet to 5 feet in no time at all. That doesn't make sense. It turns out that that most of the familiar functions are continuous at every number in their domains. From the appearance of the graphs of the sine and cosine function, we would certainly guess they're continuous, right? We know from the definitions of sine of theta and cosine of theta that the coordinates of the point P in this graph right here are cosine theta, sine theta, right? Remember your unit circle. As theta approaches 0, we see that P approaches the point 1, 0. And so cosine approaches 1 and sine of theta approaches 0. All right. Thus, the limit as theta approaches 0 of cosine of theta equals 1. So these are just some good properties to know. Just going to help you out later. And the limit as theta approaches 0 of sine of theta also equals 0, or equals 0. Since cosine of 0 equals 1 and sine of 0 equals 0, the equations in 6 assert that the cosine and sine functions are continuous at 0. Okay? All right, the addition formulas for cosine and sine can then be used to deduce that these functions are continuous everywhere. So sine and cosine are continuous everywhere. And we just said we had that theorem up above. We said if we can divide those two continuous functions, as long as there's no 0 in the denominator, then the whole function is now continuous, which means tangent is continuous except where cosine equals x, right? I'm sorry, equals 0, where cosine of x equals 0. Then we have those asymptotes. All right, so theorem 7. Again, something you definitely want to make sure you know. The following types of functions are continuous at every number in their domains. Polynomials, well, we've talked about those. Rational functions, continuous everywhere except where you'd have a 0 in the denominator. Root functions, depending if it's even or odd root, right? You got some things to check out. Well, actually, let's talk about that. Root functions. So if we have an even root, right? Square root of x, remember the domain must be greater than or equal to 0, right? Okay, you can't take the square root of negative numbers unless we're in the complex plane, but that's not for now. All right, and that's for any even. Okay. If you're taking any odd root, the domain is all real numbers. Okay? All right, that's important stuff to remember. Let's see. All these other ones are also continuous at every number in their domains. Trig functions, inverse trig functions, exponentials, and logarithmics. Okay? So let's use this information to figure this one out. Where is this function continuous? So we've got natural log of x plus the inverse tangent of x over x squared minus 1. Okay, so natural log of x, right? We want to figure out its domain. Okay, well, natural log of x, if you know the graph, it's easy, but we can convert this. Remember that loop around procedure? So this is log base e of y, well, let's call this equal to y equals x. Either way you want to put it. No, what am I doing? This is where I'm messing up. There we go. E to the y equals x. There we go. I thought that looked weird. Either way you look at it, right? So e is a positive number, right? If you take it to any exponent, you can't even get a 0. You can't get any negative. So the domain here must be x greater than 0. Okay? All right, so that's that first part here. Now let's look at inverse tangent of x. All right, if you know that one, good for you. If not, now you know. Inverse tangent of x, the domain is all real numbers. All right, look at that denominator up there, x squared minus 1. That's a polynomial. We know the domain of any polynomial is all real numbers. All right, but we've got to look at the entire function as well, right? Even though we have all real numbers, and anything greater than 0, the problem is we may have some issues with that denominator up there, right? So let's find f of x's domain. Well, again, we know that process. Take the denominator, set it equal to 0. And let's see, we'll square root both sides. X equals plus or minus 1. Don't forget that plus or minus 1. Well, actually, let me write it like this. Minus 1 and positive 1. Minus 1 we can throw out, right? Because we know, because of natural log of x, x must be greater than 0. Because this is where all these domains overlap. Okay? All right. So where all these domains overlap, must be greater than 0, cannot be equal to positive 1, right? And cannot be equal to 0 either. So it's going to be from 0 to 1, union with 1 to infinity. Okay? Because we put all these domains together. It's where they overlap. Okay. All right, let's see. Another way of combining functions, combining continuous functions, f and g, to get new continuous function is to use composite, right? Composing functions. This fact is a consequence of the following theorem. So if f is continuous at b, right? So b is this limiting value, and the limit as x approaches a of g of x equals b, then the limit as x approaches a of f of g of x, the composed function, equals f of b. Okay? In other words, the limit as x approaches a of f of g of x equals f of the limit as x approaches a of g of x. Okay? Just another shortcut again. Okay, so they want us to use that, and let's evaluate the limit as x approaches 1 of arc sine of 1 minus rad x over 1 minus x. Well, arc sine, we should know that one, right? That's just inverse sine. All right, so remember we had that limit law where we can take the limit inside here and then apply it to the outer function, in this case inverse sine. The problem is, so let's see. Inside the parentheses here we do have a rational function, but the problem is 1 is not in the domain. We'd get a 0 in that denominator, right? So remember what we said. If we have that problem, we can simplify, right? And then try it again, see if we can plug in. Well, we can simplify this fraction, right? You're thinking, wait a minute, the old man's messed up again. Well, hold on. I'm going to argue with you guys for just a second here. I'm going to say that 1 minus x is a difference of squares. And you're like, oh yeah, he's really off his rocker now, right? 1 minus x is a difference of squares. Let's use a different example. Let's see, I don't know, 1 minus x squared. You'll definitely agree with me, right? That's a difference of two squares, right? 1 minus x, 1 plus x, correct? Okay, you agree with me there, right? Then why don't you agree with me that 1 minus x is also a difference of squares? Can I do this? Well, I'm not going to ruin the surprise for you. Let's do this. What goes in that those two blank spots, right? What about this? Radical x. Try it. Foil this together. I guarantee you get this guy right here. Okay? So again, this is calculus. We're looking at things in a different light, things that you might have taken for granted before. All right? You got to open your eyes. You got to look at things differently and realize there may be other ways to do stuff. Okay? So that's what we're going to do here. So we're going to limit as x approaches 1, inverse sign. Now we're going to simplify. 1 minus rad x, 1 minus rad x, 1 plus rad x. All right, that reduce away. Remember, don't say cancel because cancel means 0. These reduce away. Okay, now if we plug a 1 in, do we have a problem with domain? We do not, right? Because plug a 1 in there, you get a 2 on the bottom, so you get 1/2. So this is the limit as x approaches 1 of inverse sine of 1/2. A lot of work, right? Man, I'm getting tired just doing all this writing. Okay, well, we did problems like this. What is the, so 1 is in the domain of this function, okay? So let's figure out what that value is when we plug in a 1, all right? Which we just did. Oh, my mistake. I made another mistake. Good Lord. There we go. I plugged in, right? So remember, when you plug in, drop the limit notation, right? I was just checking to see if you guys were paying attention. That's all right. All right, so we've done this type of problem before. So inverse sine of 1/2, well, that's, I don't know, something. Let's call it y. Which means sine of some angle y equals 1/2, right? Okay, so we've got positive sine value, right? Positive 1/2. So that's in, sine is positive, ASTC, remember? In these two quadrants. Inverse sine has a range in quadrant 1 and 4. Okay, so the overlap is quadrant 1. So our triangle lives in quadrant 1. All right, there's angle y right there. Sine from SOHCAHTOA, right? Sine is opposite over hypotenuse. So hopefully your knowledge of 30, 60, 90 triangles comes into play here, which means that's rad 3. So now you got to think a little bit. What angle is y? Y is the 30-degree angle. But remember, we're in calculus now. We don't answer in degrees, we answer in radians. So 30 degrees is pi over 6. And there we go. A lot of work, huh? Okay, again, you need to show this kind of work. Show me everything you got. Show me what you know so you get full credit. Okay? All right, we're getting there. All right, intuitively, theorem 8, so that's the one we just did up there, is reasonable because if x is close to a, then g of x is close to b, and since f is continuous at b, if g of x is close to b, then f of g of x is close to b, f of b. Another theorem here, make sure you know this one. If g is continuous at a, and f is continuous at g of a, then the composite function f of g is also continuous at a. Okay? All right, an important property of continuous functions is expressed by the following theorem, whose proof is found in more advanced books on calculus. In other words, we're not going to prove it. Not yet, but you will if you're a math major, science major, engineering majors, even most of you, you'll take a class called real analysis, and then you will prove this. Have fun. The intermediate value theorem. Think of the words. Intermediate value theorem. They're talking about something that's happening between two values. Suppose f is continuous on the closed interval from a to b. Remember that interval from a to b are x values. And let capital N be any number between f of a and f of b. So that's between your y values, where f of a is not equal to f of b. Then there exists a number c in a comma b. That's the open interval from a to b, those x values not including the endpoints, such that f of c equals n. Okay? So you're like, huh? Well, let's do a little example here. Let's look at this. So right here, this is the best way to say it. Okay? We said n must be between f of a and f of b. It's just some value. Like, I don't know, who cares? 1, 2, 3, let's call it. Okay? All right. So we have a continuous function, right? I can draw this function without picking up my pencil. So let's say we've got f is continuous on the closed interval from a to b, right? So from this point to this point, we're continuous. N is between f of a and f of b. And f of a and f of b are not equal, clearly, right? They're two different values. Then there exists some number c. So in other words, right there's c. Between a and b, such that f of c equals n. There it is. So if we plug this value into the function, we get n. F of c equals n. And there you go. The intermediate value theorem. All right. Of course, this function has to be continuous. The intermediate value theorem is not true in general for discontinuous functions. There could be a hole there if it's not continuous, right? Then it wouldn't work. All right. So the intermediate value is mostly used, or at least at this level, to show that there exists a root to an equation between two certain x values. So we have this polynomial. Show that there's a root between x equals 1 and x equals 2. Again, these are x values. Okay? All right. Well, if there's a root, remember root means x-intercept, right? Okay, or 0. In other words, we're gonna say, we're gonna let n equal 0. That's what we want to find, that there is a root, that there's some n value in there equal to 0. We know f of x is continuous since it's a polynomial, right? Again, you got to write all this out. You got to show that you know what you're talking about. Since it's a polynomial on the interval from 1 to 2, okay? We'll use closed brackets because we want to follow the theorem. There we go. All right, so let's check this out. Let's do it algebraically, and then we'll look at it graphically. So let's see, f of 1, because we want to check, right? Remember our theorem says f of a must not be equal to f of b. So f of a, this is our interval, a to b, right? A, b. All right, so f of 1, if we plug a 1 in here, we get -1, which is less than 0. If we plug a 2 in, that's our b value, the other endpoint. Plug a 2 in, you get a 12, which is definitely greater than 0, right? Positive. Okay, so thus, we chose n to be 0 because we want to show there's a root, an x-intercept, right? A 0. So f of 1, so in other words, 0 is between, darn notation. Here we go. So our n value is between f of a and f of b. All right. So thus, by that formula, by that theorem, thus, there exists a number c. between 1 and 2 such that, so ST means such that f of c equals 0, right? So this theorem doesn't tell us what that c value is. It doesn't tell us what the x value is where this root exists, right? Where this x-intercept exists, but it definitely tells us there is one because we followed the theorem step by step, okay? So we're going to write this little extra thing, therefore, by the intermediate value theorem, because I don't want to write that all out, and you're allowed to write IVT as well, by the intermediate value theorem, f of x has at least one root between 1 and 2, x values of 1 and 2. We say at least one root because it just shows there's got to be at least one place by this intermediate value theorem where there's a root between 1 and 2. Okay, you could graph this to show something else, but there may be more, there may not, right? Okay, I said we'll do this algebraically, which we just did, but let's look at it graphically as well, especially this part in here. Right, we're saying we chose n to be 0 because we want a root. We know f of 1 is -1 and f of 2 is 12. So let's just, this is just like a crude graph here. So here's, and again, this is not to scale, obviously. There's -1, there's positive 12. That's f of 1 and f of 2. We definitely know that's 0, right? So we know we have a value here. We know we have a value here, right? There's 1, there's 2. Well, since we have a continuous function, because this is a polynomial, we have a continuous function to connect those two dots, and I'm just going to draw it. Doesn't matter what it looks like. Whatever I do, it has to be continuous. I have to connect those dots with a single line. And there we go. That shows, oops, we have to cross the x-intercept, which proves there is a root. Okay. All right. Thank you very much.